To get into the proof of Rolle's theorem, I think it would be good to look at a picture. So here we've got 2 points. We're going to consider a function that has equal function values at 2 inputs, a and b. And there are basically 3 possibilities. Number 1, the function is a constant function that is horizontal through a and b. Number 2, there's a value in between a and b such that the function has an output that is bigger than f of a and b. Or we have a dip, so there's a function value in between a and b that is smaller than f of a and f of b. Anything else that could happen between these 2 points, like maybe it wiggles a whole bunch, it's a combination of these 3 cases. A lot of times in math proofs, what we do is we break things down into all the possibilities, and we call them cases. So case 1, f of x is equal to k, a constant. Well, then f prime of x is equal to 0 for all x in the real numbers, and we are done with this case, because the derivative of a constant is 0. Case 2. F of x is greater than f of a for some x in the interval, the open interval between a and b. By the extreme value theorem, f has a maximum value on the closed interval from a to b because f is continuous. Now, since f of a and f of b equal each other, and since for this value x, f of x is greater than f of a, the maximum must be somewhere on the open interval from a to b. It's not going to be at an endpoint. We've already said there's a place where the function value is higher than f of a and b, or f of a and f of b. If I have a maximum on an open interval, then I know that f has a local maximum on the interval from a to b, the open interval. Let's say that that local maximum is at c. Now let's go back to our hypotheses. We've used that f is continuous, and we've used that f of a is equal to f of b. But remember, f is also differentiable by assumption. Since f is differentiable at c, we know, do you know where I'm going with this? F prime of c is equal to 0 by Fermat's theorem. That's the conclusion we wanted. F prime was equal to 0. That does it for case 2. For case 3, we really just switch this inequality so that f of x is less than f of a. And then instead of a maximum, we call it a minimum. And then proceed as in case 2. That proves Rolle's theorem. Let's go ahead and move right into the mean value theorem now. The mean value theorem starts out kind of like Rolle's theorem. Let f be a function such that, now our hypotheses are that f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, and that's it. Then there's a number c between a and b such that f prime of c is equal to the average rate of change between a and b. So f of b minus f of a over b minus a. Let's look at a picture. All right, here I have a function f that goes through 2 points, a f of a and b f of b. Now, the average rate of change, f of b minus f of a over b minus a, that is a segment that connects these 2 points. And what the mean value theorem says is there's a place between a and b where the derivative is equal to that average rate of change. In other words, there's a place where the tangent line is parallel to the secant line between AF of A and BF of B. This is kind of like somebody took our picture from Rolle's theorem, tilted it, and added a tangent line to it. All right, let's get rid of that. Our basic path here is that we're going to create a function, apply Rolle's theorem in such a way that'll lead us to the conclusion of the mean value theorem. First, we're going to start with the equation of the secant line. Oh, let me say this is the proof. There we are. We're going to start with the equation of the secant line through a f of a and b f of b. It's going to be y equals f of a plus slope f of b minus f of a divided by b minus a times x minus a. This may look familiar from the linearization of f at a. It's not a limit here, but similar. Now the function that we're going to create is, we're going to call it h. Let h of x equal f of x minus y, where this is y. So h of x is equal to f of x minus the quantity of f of a, so we're going to distribute, minus slope f of b minus f of a divided by b minus a times x minus a. What we've done is we've taken the expression that defines y and replaced y in h of x. Sometimes folks will ask me, where's h of x in this picture? It's a good question. F of x is the curve, and y is the blue segment. I mean, really it's a line, but we're only looking at the segment. So f of x minus y is the vertical distance between the curve and the secant line. Okay. We created a function. Now we're going to apply Rolle's theorem. Rolle's theorem, you may recall, has three criteria, or three hypotheses. One is that h is supposed to be continuous, and it is continuous on the closed interval from a to b because it's the difference of continuous functions. Y is a linear function, and f is continuous by assumption. H is also supposed to be differentiable, and guess what? It is. It's differentiable on the open interval from a to b because it's the difference, again, of differentiable functions. Y is linear, f is differentiable by assumption. And then the third hypothesis of Rolle's theorem, we need h of a to equal h of b. Let's go up here. Here we have h of x. I'm going to substitute a in place of x, and then I'm going to substitute b in place of x. For h of a, f of a subtracts with f of a minus a is equal to 0, h of a is equal to 0. For h of b, we have b minus a divides out. This negative distributes. Negative f of a plus f of a, f of b minus f of b, whole thing equals 0. Now we know that Rolle's theorem is satisfied. Therefore, by Rolle's theorem, there's a c in the open interval between a and b such that h prime of c is equal to 0. Remember, we're talking about h. So let's get h again and then differentiate it. H prime of x is equal to, well, the derivative of f is f prime. The derivative of f of a, that's a constant, so it goes away. And the derivative of this slope times x minus a is just the slope. Now, for h prime of c to equal 0, that would imply that f prime of c is equal to, f prime of c minus the slope, f of b minus f of a over b minus a is equal to 0, which means that f prime of c is equal to f of b minus f of a over b minus a as expected. Now that result in and of itself maybe doesn't seem that exciting, but the mean value theorem is used in a lot of stuff throughout the rest of a calculus sequence. I want to take a moment now, though, to talk about math. In particular, I want to talk about mathematical theory, or how math works. Before you took this course, you saw the definition of a function. Then you started calculus, and you saw the definition of a limit. It was the limit of a function, right? Then you saw the definition of a derivative of a function, which involved a limit, and the definition of continuous, which says that the limit value equals the function value. Then we saw the definition of a local maximum and a local minimum, and absolute max and absolute min in the extreme value theorem. Then we saw Fermat's theorem, which connected the idea of a local max or min with the idea of a derivative. You saw several of these things referenced max, min, extreme value theorem, continuous, differentiable, and Fermat's theorem in the proof for Rolle's theorem. And then Rolle's theorem was used to prove the mean value theorem. This building block, or all these building blocks here, this is how math works. It starts with definitions. We move on to theorems, and then we use results and definitions to develop future results.